Okay, so now we have to obviously redefine our second law of thermodynamics. And Gwen gets to do that.
Oh, yay. Okay. In nearly all systems where the system has enough particles and units of energy so that we can apply the statistics of very large numbers, the particles and the energy of the system tend to rearrange themselves until the multiplicity is at or very near its maximum value. Hence, we can redefine the second law of thermodynamics as, in any large system, the multiplicity tends to increase, and at equilibrium, the system will be found in the macro state with the greatest multiplicity.
Can we read that all together, please?
You're killing us.
It's important. It's really important.
3, 2, 1. In any large system, the multiplicity tends to increase, and in equilibrium, the system will be found in the macro state with the greatest multiplicity.
Since the multiplicities tend to be very large numbers, we work with logarithms instead, and the entropy will be given by equation 11.17. In general, the number of particles in a system is directly proportional to the energy of the system. This implies systems with a large number of particles will have larger multiplicities and hence larger entropy values.
11.545. Why I do not like to think entropy as a disorder? Some people find it useful to think of entropy as a disorder in the system. But what is a disorder? We all agree that a shuffled deck of cards is more disorderly than any sort of.
Do we?
I hope so.
Okay.
Cool.
Just making sure, right? Is that our definition of disorder? We shuffle a deck of cards.
It's not in order.
Yeah.
Yeah. Okay. This means that shuffling increases the entropy because it increases the number of arrangements of the system. This is simple enough. On the other hand, if we take an equal amount of water and crushed ice, a glass of crushed ice will appear more disorderly. However, water has more multiplicity and hence a larger entropy. Because there are so many more ways of arranging the molecules and so many more ways of arranging the larger amount of energy between them. So I like to think about entropy as a possible number of arranging the microstates instead of thinking of entropy as a disorder.
Do you guys get that?
Yeah.
Because when you have crushed ice, what it is there's fewer ways of arranging those molecules, right? Because part of them are stuck. But if you have water can just fluidly move anywhere. It's like almost like having a gas, right? So if you have gas, it can just move wherever it wants. So I tend to not think of it as disorder. I think of it in terms of how to arrange things. Get it? Okay. So what is a nice property of entropy? Casey, do you want to continue? Yes, please.
Sure. The total entropy of a composite system is equal to the sum of the entropies of its parts. Suppose the system is made of two parts, A and B. The total entropy of the system will be the sum of entropies of part A and part B, assuming macro states of A and B systems have been specified separately.
And this can only be done if you use properties of log.
S total equals KLN omega total. And you want me to just keep going?
Yeah, so K log of omega A plus omega B, omega total will be omega A times omega B, which you can use the properties of log, right? Everybody knows properties of log. Anyone need a refresher?
Can I continue?
Yes, please continue reading.
If systems A and B interact with each other, then the macro states A and B can fluctuate over time. And to calculate the entropy over long time scales, we have to compute omega total by summing over all the macro states of the two systems. Entropy, like multiplicity, is a function of the number of accessible microstates, and this number depends on the time scale under consideration. However, in practice, the distinction rarely matters. Just assume the composite system is in its most likely macro state and gets essentially the same entropy as if we were summing over all macro states.
Excellent. Okay, so now how do we solve problems? So actually we should all read this together. Steps to follow when solving problems.
Why don't you have someone with a loud voice read it?
I will read it. I have the most annoying voice. Steps to follow when solving problems. So step 1, use 11.16 to get multiplicity. What is 11.16? I would write that on your note card. That one. So use this to calculate the multiplicity. Number 2, find the log of the multiplicity if you found. Basically, just plug it into your calculator and simplify as much as possible. If not, use multiplicity for a large number. And when you try to find the factorial, you may get an overflow problem with your calculator. Fortunately, there is a good approximation called Stirling's approximation for log of n factorial, which is log of n factorial is approximately equal to n log of n minus n. Once you have log of n, use this equation, S equals K log of multiplicity, to find entropy, maximize the entropy to obtain the preferred distribution of quantum states. Duh. Oh, and I also want to make sure that you guys know, it is interesting to note that the Stirling approximation and the one that invented the Stirling engine are not the same person. So do not confuse that. They are two different people.